Okay, now let's return to the very first problem that we did, and let's talk about how we can solve this problem. Before I get into that, let me explain to you why we're solving the problem this way. It turns out that it can be proven that this problem, the original problem we're given, and this dual problem that we came up with actually have the same optimal solution. Now, when I say optimal solution, I'm only talking about for the objective function. So the value that minimizes this function, in other words, the minimum of this function for this original minimization problem and the maximum for this dual problem are actually the same value. Now, they don't occur at the same points, so we have to be a little bit clever when we interpret the solution. But it turns out that the minimum of this problem and the maximum of this problem are exactly the same number. So we won't worry about why that's true, but just trust me that it is. You could actually graph these two problems and solve them both by graphing and see that the minimum of this and the maximum of this function are actually going to be the same value. Okay, so let's return to this dual problem. Now, let's see how we solve this. Since this is a standard maximization problem, we should be able to solve it using the simplex method. So we're going to solve this problem by the simplex method, but there's going to be one catch. When we add slack variables to these constraints to turn them into equations, we're going to bring in the variables from the original problems. In other words, when I add a slack variable to this constraint to turn it to an equation, I'm going to use not S1, but I'm going to use X1. So I'm going to add X1, where X1 is the decision variable from the original problem. And then for my second constraint, I'm going to add X2. So we're going to add X2. And there's a good reason for that, but you don't need to worry about it right now. Now remember, now that we're trying to set up the initial tableau, this is where we move these terms across the equal sign. So if we move these to the other side, they change sign. So that's going to be minus 15y1 minus 20y2 plus p equals 0. Now, you know how to write this in a tableau now. So notice over here, I've written the initial simplex tableau. Now notice that I didn't list the basic variables over here because you really don't need to worry about what the basic and non-basic variables are when you're solving a dual problem. So let's just go ahead and get to it. We're going to use the same method though as before, the simplex method. So let's drop down here and let's look at this tableau. Notice that -2 is the most negative indicator, so this is going to be my pivot column, this second column. And then when I divide 2 into 5, the quotient is 2.5, and when I divide 1 into 2, the quotient is 2. And since the smaller of those two quotients is 2, that means that the second row is my pivot row. So the second column and the second row intersect at this number here, 1. Now, just like we did before, once you get your pivot element, you want to use that pivot element to eliminate any values above and below it. And we're not going to worry about the arithmetic here, so I'm going to assume by now you know how to do row operations. But to eliminate the 2, I'm going to multiply -2 times row 2 and add it to row 1. And that will change that 2 to a 0, and of course it'll change some other values in row 1. And now to eliminate the -20, I'm going to multiply row 2 by 20 and add it to row 3. and that'll give me the 0 here. And so now we'll have a 0 there. Now, notice now I don't have any negatives on the bottom row. So I don't have any, since I don't have any negatives, then I must have the optimal solution. Now, let's talk about P first. P, we can see here, is 40. Well, if P is 40, well, that's the solution to the dual. Then remember what I told you, if the maximum for the dual is 40, then the minimum for the original problem must also be 40. But the trick is, we don't care about these y values. Normally in the simplex method we would say, well, y1 is non-basic, so it's 0, and y2 would be found here to be 2. But we don't care about y1 and y2. We want to know what x1 and x2 are, because those were our variables from the original problem. So what we have to do, let me show you what we have to do. This is kind of sneaky, but let me see if I can pull it off. Okay, so normally when we solve one of these problems before, we always look to the far right to get our answers. But remember, to get to this dual problem, we kind of rotated the problem to the right by transposing it. So let's see if I can rotate it back to the left and see what happens. All right, let's see, where am I? Here we are. So now here's the problem. Okay, I kind of rotated it back to the, so I rotated it back. But look here at x1 and look to the far right of x1 and you have a 0. Then look to the far right of x2 and you have a 20. So x1 would be 0 and x2 is 20. Now actually, to clear that up, if that confused you, the point is, all you really have to do to find the solution to the original problem is look below at the very bottom of their column. So the solution for x1 is found at the bottom of the x1 column. The solution for the x2 is found at the bottom of the x2 column. Okay? So again, we don't really care about these y values. What we care about is this c value. That c is 40, and you can see that x1 is 0 and x2 is 20 because that's found at the bottom. So the solution to the original problem is the minimum value is 40 when x1 is 0 and x2 is 20. Okay, so I know that was a little confusing, so let's see if we can do it one more time and see if repetition will help it set in for you. Okay, so this is another problem that I set up the dual problem for you later. So we want to solve this minimization problem, and since I've already shown you how to get the dual, I showed you how to get this dual problem earlier in the earlier video. Let's go ahead and see how we can solve this problem. Well, you've got 3 less than inequalities here. So for each one of those less than constraints, we're going to have to add a slack variable. And remember, the slack variables have to be these variables x1, x2, and x3 from the original problem. So in the first constraint, I'm going to add x1 and then change it to an equation. And then the second constraint, I'm going to add x2, and that'll change that to an equation. And then I'm going to add x3 to the third constraint, and that'll change that to an equation. And then I'm going to take these two terms and move them to the other side, so their signs will change. Now, I didn't stagger the values here. You know, you can do that sometimes to kind of make it easier to see how it goes in the Tableau. But basically, I think you know how to put these in a Tableau now. Just probably easiest to list your columns first like this. Say, okay, column for y1, column for y2, column for x1, column for x2, column for x3, a column for p, and then save room for a column for your constants. Now, the first the first equation, it says 2y1 plus 4y2 plus x1 equals 40. The second one says 1y1 plus 1y2 plus x2 equals 12. And the third one says 5y1 plus y2 plus x3 equals 40. And then the bottom row says negative 20y1 minus 30y2 plus p equals 0. Okay, so now we're going to solve this using the simplex method. So the pivot column is obviously this second column because negative 30 is the most negative indicator. And then if you divide 4 into 40, you get a quotient of 10. 1 into 12 gives you a quotient of 12, and 1 into 40 gives me a quotient of 40. So the smaller quotient is row 1. So the intersection of row 1 and column 2 is this 4 right here. And so now what you're going to do first is you're going to multiply this row by 1/4. So I'm going to take 1/4 of row 1, and then I get that matrix. Now remember, we're pivoting on this 1 right here. Then we're going to say minus row 1 plus row 2, and that'll give me the 0 here, and of course it'll change these values. You can do the arithmetic. And then we're going to do minus row 1 plus row 3 so that I can get a 0 over here. And of course it'll change the values in that row. And then we're going to do 30 row 1 plus row 4 to get the 0 here. And then again it'll change everything else in that row. And now we have a new matrix. But notice that we are a new tableau. But notice that we don't have the optimal solution yet because we still have a negative on the bottom row. So let's just copy that matrix down here. This has to be the pivot column because that's the only negative indicator. And if you divide 1/2 into 10, you get 20. If you divide 1/2 into 2, you get 4. And if you divide 9/2 into 30, you get like 6 and 2/3. So this has to be the pivot row. That's the smallest quotient. So we're going to pivot on this 1/2. So the first thing we would do is we'd have to make this a 1. So we got to multiply everything in row 2 by 2 to make it a 1. And then once we get the 1, then we want to get rid of the half by doing minus 1/2 row 2 plus row 1. And then we want to do minus 9/2 row 2 plus row 3 to get rid of the 9/2. And then 5 times row 2 plus row 4 to get rid of the negative 5. And of course that'll give me a 0 here, here, and here. And now notice I have no negatives on the bottom row. So now I can look at the bottom row and determine the values for x1. Notice x1 is 5. For x2, let's look at the bottom row. x2 is 10. And for x3, the bottom row for that column is 0. And then since p is 320, then c must also be 320. So x1 is 5, x2 is 10, x3 is 0, and c is 320. This last problem here, I'll leave you to work it, but here is the dual problem. And of course you can see over here I do the initial system, and then I put it in tableau form, and I find my pivot element, and then I do the row operations. And I didn't list the row operations, but the row operations to make that a 1 and all zeros. Then I still have to pivot again because I still have a negative. So this is my pivot column, and then I get my quotients and figure out that this is my pivot element, and then I do the row operations to make that a 1 and eliminate everything else in the column. And then when I get to the end, notice that at the bottom of the x1 column you get 0, at the bottom of the x2 column you get 3, and at the bottom of the x3 column you get 5. And then since p is 44, then c must be 44. So that's the optimal solution. I'll do a little quick video add to this because I want to show you a neat application problem or two for this dual method. So there'll be a third video with this, but I don't think it'll be a full-length video. Okay.